Last time in the prelude to part 1, we found our intrepid but dishonest pitchman Fred R. Slick hawking relabeled table salt as Fred's secret formula table salt. The main event was our enthusiastic but equally clueless reporter Skippy Fredrickson in vintage video interviewing reputedly the oldest chemistry teacher in the world, Al Chemist. Dr. Chemist helpful in explaining acid-base chemistry, but having anger issues, beating Skippy about the head with a book most of the time, and the only voice of reason, Sonny the Canary.
Why, sure, there's other definitions for acids and bases. One of them was come up with by a favorite student of mine, Arrhenius. Now, he has his traditional definition of acids and bases, where an acid increases the hydrogen ion concentration in an aqueous or water solution, and a base increases the hydroxide ion concentration. Don't you think so, Sonny? I say so too. Now, Bronstat and Lowry, their definition, students of mine also, same class, called an acid a proton donor, a base a proton acceptor. So, what is a proton anyway, except for a hydrogen without its electron? So it's a hydrogen ion. So a hydrogen ion and a proton are really two ways of saying the same doggone thing. Now, the broadest definition of acids and bases would probably be the Lewis acid-base concept. Lewis, another favorite student of mine, he did really well. So anyway, a Lewis acid is an atom, an ion, or a molecule that accepts an electron pair to form a covalent bond. Then a Lewis base would be an atom, ion, or molecule that donates an electron pair to form a covalent bond. All this donate and accepting and all this stuff gets kind of confusing, doesn't it, Sonny? Think so? Sure. Why, sure, there's a difference between strong acids and weak acids. A strong acid or base would be something that completely disassociates in water, just breaks completely down into protons and anions or hydroxide ions and the cations. You've got weak acids or bases, like a weak acid would be like vinegar, where it disassociates to some degree in aqueous solutions, but not completely, so it's not as strong as a strong acid. Okay, so you're interested in pH scale. Basically, that's powers of hydrogen, okay? So the pH scale goes from 0 to 14. With being in the 1 range there, you're talking about an acid. Being in the 14 range, you're talking about a base. And in between, like a number 7 pH would be neutral. Okay, so you can always remember that lower pH scale, that's acid, so A comes before B, acid before base. You get there, young man? Good. Okay then, to calculate pH, fairly simple. It's the negative log of the hydrogen ion concentration in molarity. Molarity being moles per liter.
So again, to calculate pH, you take the negative logarithm of the hydrogen ion concentration of the solution in molarity. For instance, if your hydrogen ion concentration was 10 to the negative 7th, your pH would be 7.
Gee, Dr. Chemist, seems like we're doing pretty well now. Can you tell me about one more thing? I think it's called a buffer. What? You say suffer? You want to suffer? Well, son, I think you ought to just do it yourself. It'd really just be easier. Here you go. Oh, that's gotta hurt. Buffer. You want to know about what a buffer is? Well, a buffer is a special solution that can resist change in pH. Now, you can add a lot of acid or you can add a lot of base, it still doesn't change. It stays right at the range it was originally. A good example of a buffer would be the blood in your body. Now, I know, you silly little man, you seem to be a waste of so much good chemistry, but nevertheless, the addition of acid or base to your bloodstream doesn't affect it. It's a buffer. It stays right at the pH it's supposed to be. We could go into more detail on a buffer, but basically a buffer contains a weak acid and the salt of that weak acid. And that combination lets a buffered solution stay right in the narrow range that it's supposed to be at.
Let's review. Acids taste sour, bases taste bitter. Both change the color of acid-base indicators. Both conduct electricity in a water solution, an electrolyte. When acids and bases react, they produce a salt and water. This is a neutralization reaction. Table salt, sodium chloride, is a salt, but not the only one. Once again, let's look at these definitions. The common definition of an acid and base would be acid being a hydrogen ion donor, base being a hydrogen ion acceptor, or a hydroxide ion donor. Arrhenius or traditional. Acid increases the hydrogen ion concentration. Base increases the hydroxide ion concentration. Bronsted, acid is a proton donor, base is a proton acceptor. Lewis definition, acid accepts an electron pair to form a covalent bond, base donates an electron pair to form a covalent bond. Again, let's look at the strength of acids and bases. Strong acids and bases break down 100% in aqueous solution. Weak acids or bases only partially break down in water, not completely like strong acids and bases do. pH scale, generally it's 1 to 14. 1 to 7 is acidic, 7 to 14 is basic, 7 in the middle is neutral. Again, the definition of pH is the negative log of the hydrogen ion concentration in molarity. And buffer, a solution that resists change in pH when acid or base is added. Solutions can be designed to stay at a particular pH by the addition of the correct weak acid and their salt.
Fred R. Slick. Acids have a sour taste, but don't you go... I know you have it already. You're right. Why, sure, there's a difference between... Not only is he the oldest living... Not only is he... Oh, silly old man.
ARF.